What is the difference between a differential rate law, which can also be called your general rate law, versus the integrated rate laws? Well, to begin with, your differential rate laws are simply a rate which is expressed as a function of concentration. You can perform some calculus on them. You can integrate these rate laws to make it so they become a function of temperature. So here is your zero order rate law at the top in the top box. When you integrate it, you would move the partial dt, so just replacing a d for your little delta sign. You'd move your dt to the right, take the integration of both sides of that equation. That turns it into our integrated rate law, which you see at the bottom. You can perform similar calculus on your first order reaction using the idea that the integration of 1 over x dx equals ln of x plus a constant. Or you can do the same type of thing on your second order rate law. And so if you care about the calculus, talk to me about this outside of class, come talk to me, or just sit down and work these problems yourself. It's quite fun to see how do the general rate laws get translated into integrated rate laws. But at the end of the day, you have these three integrated rate law functions here, shown here, for zero order, first order, and second order. And these integrated rate laws are very helpful when we're trying to analyze some of our reaction rate data. It just depends on what the data looks like as to whether or not you're going to analyze them using integrated rate laws or differential rate laws. So, first off, why would we want to do this? All right, great question. I'm glad you asked. Well, here are some graphs of the different differential rate laws. You have a zero order, which means your rate equals your constant, and so you're constantly decreasing. Your initial concentration of your reactant is constantly decreasing until it runs out, okay? And so it's got a straight line, but it's going downward. You can't really tell much about it. Your first order, it starts out as concentration and then it decreases, but it decreases at a rate equal to your constant times your concentration. Your second order is decreasing, but at a much quicker rate, especially at first. And so you get these nice kind of curved off expressions and graphs. Wouldn't it be nice if we had our calibration curve, which you see here, and then we test an unknown and we have a signal for that unknown? Normally we would just put it in the calibration curve and then go down where you see the star, and that would tell you, oh, here's the time. So whenever you have a calibration curve, it either lets you predict what's going to happen at future time, like you see here, or if your x-axis is concentration, it allows you to determine the concentration of an unknown. But that is on the basis and the premise that you've got a trend line which accurately reflects the data given. You can fit your curve to some type of line, it's just not linear. And so the idea would be if we integrate these differential rate laws, we can force these graphs to be linear so that way we can graphically analyze unknowns or predict what's going to happen at a given future moment in time. It's a lot more accurate than applying these expressions that you might have for these differential rate laws. And so why would we want to integrate the differential rate laws? Oh, to make predictions and analyses easier, because now we've got a linear trend line. What do I mean by a linear trend line? Remember, y equals mx plus b. Your y variables equals your slope times your x variables plus your intercept, your y-intercept. By integrating the differential rate laws, you can take those graphs that you see here and you can turn them into linear graphical plots. How might you say? Well, we want to just make it easy and we want to use this y equals mx plus b concept, where your y-axis that you see here, if we graph that versus our x-axis, which is going to be our time for all three orders, we can have a nice y equals mx plus b format, where your slope is related to your k, but notice how on zero order and first order, they're both negative. So you have a negative slope, so that means your line is going from the top left to the bottom right, it's going negative, whereas a positive slope means you're starting at near the origin, somewhere near there, and you're going up and to the right. And so what this tells us is we're able to determine both our intercept, which you see here in blue, and our k's, our rate constants, which you see here related to the slope, if we graph the right thing. What do I mean by that? Well, I need to make sure I choose what I'm graphing on the y-axis appropriately. So I have these highlighted in orange for you. They're also circled here on these graphs. So notice in zero order, you have to graph concentration versus time. For a first order plot, you have to graph the natural log of your concentration versus time. And for a second order plot, you have to graph 1 over your concentration versus time. And if you do that, every single one of these reaction orders should give you a linear plot. Now, any reaction is not going to be zero first and second order. It's just going to be one order type. And so remember, you can't determine these differential rate laws by looking at stoichiometry. We can only determine them using experimental data. And so what you can do for integrated rate law is you can similarly figure out an experiment and design an experiment that can allow you to get the same type of data from it. And so what you've got is you can just graph the concentration versus time, or the natural log of the concentration, or 1 over the concentration versus time. And if that gives you a linear plot, then you know it's zero order, first order, or second order. How can we tell the difference? So before we go into examples on how do I determine reaction order from experimental data, I just want you to be able to look at the two and think about what is the difference in them. So your differential rate law has one format where we're graphing the rate, or we're looking at the rate as a function of concentration, whereas your integrated rate laws are establishing concentration as a function of time. These are two intrinsically different things. And so how you look at the data is different. One is a function of time, the other is not. Another way you can tell is by what data you're given in the problem. If you're looking at initial rates, that's a differential rate law problem. If you're looking at how a concentration of an analyte, which is the thing you're measuring, changes over time, it's an integrated rate law. You might have to use concentration and time to calculate an initial rate, but then all of the data is going to be dependent upon a change in concentration with a change in time. And so you can tell the difference between these two rate laws based on either the data you are given or just the concept. Are you looking at concentration, or is time anywhere in the problem? And so whenever we're looking at the difference between these, you need to just be asking yourself the question, what is the data that I'm given? What am I asking to solve? And we'll allow that to help you figure out the difference and how to solve the problem.